like a big send-off. So yeah, this is the bipedal robot. So yeah, it kind of started with the basis of creating an artificial intelligence. So what you're looking at is only half the project. The other half was probably about the same amount of work. I wanted to make something that learned how to walk. And that's a pretty complicated procedure. So let's talk about AIs for a second. So an artificial intelligence requires, I think that's the next slide actually, I'm going ahead of myself. So an artificial intelligence is basically a function or a program that's supposed to do something on its own. A function or an action, it's supposed to do something. I created this AI on the basis of walking. That's just an example, we'll talk about that later. And an AI is generally composed of two different components. First of those components is a purpose. So these are two examples of AIs that you'll find in the world. First one is a self-driving car. That's not like one of the Google cars. At least I don't think it is. I think that's something someone made at home. Probably very illegal. So it's designed to drive. The second picture right there is a robot designed to play chess. Now, an artificial intelligence, how it differs from something like a general intelligence is that it's only designed to do one thing. So if you were to take that chess driving robot and you were to put that in that car seat, it wouldn't do much. That's not just because of physical limitations. If it was able to drive the car, it might do something like go up 2 streets and a street to the left, because that's what a knight does in chess. It doesn't know how to do things. The second thing that it needs is a model of reality. So the robot needs, or the artificial intelligence needs something as a basis for which it can operate. So it needs to know what the world it's in. It needs to know the world that it's in. So if you're to create something that's, let's say, as smart as a human would, it would need to be programmed with things like ethics and morality and things that are, frankly, very, very, very tough to quantify. So if you were to have an artificial intelligence that would be like a helper robot, and a burglar breaks in, and the burglar starts attacking the family, the robot's going to sit there and it's going to say, what do I do? Now, if the model of reality for that artificial intelligence was perfect and it was programmed, it might defend them, it might try to stop any sort of violence from happening whatsoever, but that's still a very tough thing to quantify. Now, with the case of my robot, it generally works off of, its purpose is to exist, and then it's to go. And that can be done through any method. As long as it gets from point A to point B, the crawl there, that'd be good. The second thing is the model of reality. Now, for all intents and purposes, this is the model of reality for my AI. Nothing really exists. It doesn't have a model of reality other than a flat surface. So, ideally, you could just keep going forward, and nothing's going to stop it. Or actually, the model of reality could probably be motor extensions, and it's got a couple of senses built into it, built into the program, that allows it to know where its limbs are. So how does it work? So the thing starts with it starts off as a concept. So what happens is I have this little book, and I write down what I want it to do. So the very first thing that I ever designed it to do, or ever really thought of, was a leg. It's how it all starts. And from there, I break it apart into pieces. This robot uses around 50 different pieces that I have to print and then glue together and connect the gears and do all this other sort of stuff. So it starts with concept. There's a lot of math involved. That's for creating a gear. There's a lot of gears in this thing. I hate gears. Because they are very, very hard to make. You have to do radial arrays and stuff like that. And this is all built in CAD, which is computer-aided design. This particular thing is CAD-ware by Autodesk. I hate it because it's really, really tough to use. Yeah. If you have any questions, just blurt it out. I mean,
Well, I'm just curious right away, why did you choose to make everything? Why didn't you buy off-the-shelf gears and kind of stuff like that?
it's too easy. But yeah, so every single part, like this one, for example, I have to glue this on. So those actually don't do anything. That's just it was supposed to do something, and then I changed the design, which happens a lot. Is I'll make something and then I'll delete it and then I'll make another one, or I'll see that there's another better way to do it. I'll do that. So that happens a lot. So there's a lot of things that we're simply throwing out. Next thing is that they're printed. So what you're looking at right now is one of the linear actuators before I redesigned them. So I designed this thing to have 4 muscular groups. The first 2 were in the hip, the second 2 were in the thigh. The rest of the robot is controlled by gear systems, controlled by those actuators. So those are one of the actuators that are disassembled. What you find is that there are actually 4 motors in here, and each one is designed to push something. There's these linear drive rails that are connected to the shin bones, are connected to these weird hip things. These will actually just slide back and forth, and it will move the calf up and down. What's my next slide? So that's one of the linear actuators. That's just kind of like a bare bones picture of it. Creates a mess. These are all like glued together, and it basically I set them together pretty much any way I could. Gorilla Glue is the greatest thing, but I hate it. The fun fact about Gorilla Glue is that the gel stuff is essentially like pepper spray. If you like glue something with it and your head is over it, it'll like burn your eyes and nostrils like a lot. So yeah, sometimes parts didn't fit together and I had to like scrape it down or sandpaper it, and it was a really bad thing. I didn't have time to like redesign components, so I just like, whatever, jury rig it. And then you have a finished robot. That was taken at 1 o'clock last night.
Wow.
I've been working on this solid for 2 weeks. I slept like 6 or 7 hours in the last 4 days. So the program. So this is the other half of the code that was quite a feat. This is the most complicated program that I have made and that I know of. So to start off, there's 7,123 lines of code.
What language are we talking?
Arduino, so that's C++ syntax. So that's 213. Okay, so
A couple of people in the room understood that, but I think I'm punched in.
okay, I'll just do like a quick. If anything just like goes over your head,
Yeah, show us
feel
what
free
it
to
looks
just stop me.
Oh, there you go.
Spanish,
Yeah, that's. So this thing runs off of a microcontroller called Arduino, and now what Arduino does is it turns circuitry and it connects it to programming. So how it does this is it creates these pins, and if you plug a pin into it, you take that wire, plug it into a light, and then tell the Arduino through the code, turn on this pin, the light will go on. So the way it uses some programming language called C++, and that's generally what computers use. There's also Python, Java, and all these other weird types of languages that you don't really need to know about. The actual code is right here. So it uses.
Can you put it up on the screen, or that would be hard to do? Just so they can see what code looks like?
We had it on one of the school Macs the other day, so that should...
Yeah, it's on Drive. It's not the final one.
Or maybe you want to wait and do that after, so we don't mess up your presentation?
Yeah, I can show it after. It's no problem.
Okay.
Actually, I just remembered I have printouts. So you can check these out. That's actually just the first function. I was going to talk about that here. Just kind of grab a few of these. Take one.
That's what Chris does, yeah.
So I'm going to be talking about what that does.
That's kind of boring to me.
A few years ago.
So
You know that one.
Where did you learn C++?
the programming class.
Okay.
And you kind of pick up stuff. I learned a lot of it as I went on. So that's only just the first function. I'll talk about that later. But there's 7,123 lines of code. If you were to put that in a standard text document, it's 213 pages long. So if you
And
were
how
to,
much of that did you like write out by hand, and how much of that was taking chunks and repeating them?
well, a lot of it was taking chunks and repeating them. But what would happen is I would have to, go through all the variables and change them. And, yeah. So most of the function is actually just through creating. I'll talk about all that later in the function section. So 11-point font, single space, 213 pages. You were to walk into the library and you got a young adult's book. Read through it, it's 200 pages long. Imagine all of those pages just having code on them. It was a lot. It takes 5 minutes to copy and paste it, and I needed a separate add-on for the microcontroller to actually store all the code. So there's 4 motors that are controlled by the program, and there are 4 variables for a single action. First, speed, so how fast the motor is going to turn, how far the motor is going to turn, how long it's going to wait until performing the next action, and which motor is performing that action. So it's basically, so there's 1,488 separate variables. Now, a variable is just like, if I was to say, if I were to create an integer called x, and that x is equal to 4, I would say x plus 8, and then it would just do that little arithmetic, and it would change the variable. And that's how essentially things are done in programming, is those variables change, and the manipulation of those variables that do things. So there's 1,488 of those that are in this code. What you're looking at right now is probably around like a few hundred of them, or maybe not a few hundred, but the paper that I just handed out used something called an array, which is a really good way of storing integers. That's how the whole code kind of works. So if you actually look at the paper, in the beginning section, it'll have an array that has 13 items in those arrays, and there's like 20 of them. I use every single one of them multiple times. And with the code, there's at least 1,800 mathematical operations that are done in creating a single set of instructions.
What kind of, give us examples of what kind of calculations you're doing.
Well,
Are you doing more than adding?
oh yes, there's a lot more than adding. The whole code basically functions off of creating instructions from partially functioning instructions. So there's a lot of random integer operation. There's a lot of making sure that the device doesn't break itself through the code. So there's a lot of safeguards. So if those things overextend, it might hurt the robot. So there's a lot of geometric positioning that are done with all of that. And most of the math was actually done in creating the robot, in CAD and stuff like that. And theoretically, you could have an infinite number of operations if things just don't work. It'll just keep doing it over and over again until it figures out something that might work, and then it'll run that. So the first function which I handed out is called walk start, and there's several functions in the code. Now, walk start, it creates a random set of instructions, completely random. It's like 9 pages long if you were to put it in a document. It doesn't expect to do it correctly the first time. So basically, it'll just run it and run it and run it until it finds something that might work. So this is the human equivalent of a baby eating dirt. It doesn't know what it's doing, but it will do it because it's an option. And then eventually what will happen is after you run it enough, it might do something that's not entirely wrong. And then you'll say, wait, keep doing that. So,
How do you make that judgment? How do you decide?
usually, like, if it goes at all, that's good, and I'm using that. So, it'll make it starts by making a...
But how does it do it in the software, or do you manually go in and say, yeah?
If I really look here in the packet, at the very end of it, it'll have a console command that says, how was that? And there's a couple of buttons on the robot. Click
Okay,
yes,
okay.
I'll click continue, or I'll click stuff.
So you're manually inputting
Yeah.
a human assessment response to feed the next set of data and corralling based on historical experiences.
Yes, exactly. There's not a whole lot of sensors added to this other than the ones that are programmed in. Yes.
Did you like watch a video? Has someone done this before you? Did you like make all this?
I have scoured the internet. No one has made anything close to this. What I know is that if any of you know the Atlas robot or DARPA? Well, DARPA is the experimental branch of the military, and they are responsible for such things as self-driving cars, and most recently they had a robotics challenge. Now that robotics challenge had a lot of competitors, and they all failed miserably. It was a very bad challenge, but it was really funny watching them all fall. One of these robots is called Atlas, and Atlas is created by Boston Dynamics with collaboration with Worcester Polytechnic Institute. I actually traveled to WPI and talked to their head of robotics, and one of the ways that they decided to make it walk is through something similar to the evolutionary base code. Stop looking at that baby eating dog food. So it uses something similar to this. I don't know what they do. They don't release that online. So yeah, this is all done by my own hand. I designed all the pieces. I made all the code. Second thing it does is walk repair. So after it's run through that program enough and it's decided that, hey, this doesn't work as badly as the other things, I'll say, okay, choose that one. And it'll take that random set of instructions that work kind of, and it'll create a bunch of new set of instructions based off of the one that I liked. So it'll create five generations, or five sets of instructions off of that initial one. And this is where it does most of the operations in creating those new sets based off the partially functioning ones. And it'll create those 5 sets, and then it'll run those 5 sets, and it'll reset the motors, and it'll put everything back to base state, and it'll do all the overextension safeties and stuff like that, but it'll basically randomize the instructions in a certain set of parameters. And it'll do that 5 times, and I'll choose which one of those I like the best, and I'll say that one, and it'll say, okay, takes the program that I liked, puts it right back at the beginning, makes another 5 sets, closes the parameters, does that over and over and over and over again. And after each set of instructions, it'll tighten those variables, meaning that it'll make sets of instructions that are more similar to itself. So it'll basically go throughout the program, finding that perfect little sweet spot where it can do that action well. So that's where most of the code is that walk repair. And the last thing it does is once it finds that nice little set of instructions, it'll save that into a database that is at the end of the code called walk final. Now it's important to note that this program doesn't just walk. That's an example of something that it can do, but this program is essentially a basis for creating any action. So I could code it to sit down, or I could make it sit down, I can make it stand up, I can make it jump, I can make it run, I could probably make it swim if it were waterproof, but there would be no changes to the code whatsoever. It would all be the same.
How big of a set of data is in the database for what scope of motion over what period of time?
Well, as I said, there was like 1,500 variables, and what happens is there's four motors, and each of those 4 motors requires 3 variables for an action, and each of those 3 variables for an action has to be repeated up to 20 times. So there are 20 actions. You can use a multiplication, but there's a lot of variables. I can share you the code after, and you can just see the wall of arrays that I set. I
understand the arrays. I think the question that I'm asking is, there's a learning you're going after, and in the end, is that to take half a step, or is it to take 2 steps, right? Because you're going to have a number of positions. You've got a number of variables, right, that you're trying to save to. How many define success over what scope of range of motion over what time frame?
I don't really understand the question. I'm going to try to answer it. So there's 20 actions. That's the maximum amount of actions that it can do. That is programmed to do. So
So is that 20 positions on the linear?
an
Slide.
action would be declared as a speed, a speed, a distance, a delay, and a motor. And that is declared by one action. So one action might be the robot lifting its leg up. That's one action. And then there might be an action where it moves the other leg, down. And that might be another action. And it'll store up to 20 of those actions. And then depending on what I want the robot to do and what buttons I press on the robot, it might do something else. So it can run.
So once it figures out to walk, could it walk forever?
Yes.
The
So-
20 sequences of 4 data sets.
Yeah. Essentially.
So you turn it on and it figures out how to make it walk. Then
Figures out whatever I want it to do.
does it save that information somehow?
Yeah, it saves it
Built on
in
it?
the
And the next time it figures out how
And
to
it'll
walk
keep
even better?
improving that set of data. And it'll just go through different generations, I basically choose what I want it to do. That's a lot of my own decision, but in the future I might incorporate something like a couple sensors and it'll make that decision itself. So it's all stored in this walk final. And then it'll cycle the program all over again. What will happen is it'll make a new set of data, and then I can make it walk backwards, and then that'll also get saved in walk final, and I can say walk forward, okay, now walk backwards, and then it's all saving that in the code. Theoretically, I let it set up to the 5 finished actions, but it's easy to do more, just a lot of copy and pasting. So it's nice. So I made this robot as a basis for artificial intelligence. So obviously, the robot's not going to be the primary focus of it. What I want to do next after this, and hopefully in college, is I want to digitize it. I want to create simulation that the robot can exist in. And it's not a robot. This is just a Google simulation. That's what came up. It's creepy, I know. Yeah, so
Where are you going to school?
RIT. So I would make the process to creating an actual functional AI, and this was my theory at the beginning, and this is my updated theory now. I wanted to create an artificial intelligence, a fully capable artificial intelligence. And the way I would do that is I would create an infantile program much like this. And I'd say, do this as some sort of easily quantifiable goal. Then I create a new programming language capable of rewriting itself, and it will constantly write more code in for itself. So it'll just basically try everything, and then if it's closer to that goal, it'll use that. If it's not closer to that goal, it'll just start from the beginning. And when I say like a goal, it could be a military battlefield. You could make an artificial intelligence that is capable, that is designed to play a game. That game, being a simulation, could be anything we want it to be. It could be a stock market simulator. It could be a war simulator. It could be riding a bicycle. It could be doing any of these stuff. So you would make a program with a body or the capability to act on the system. But you would create that simulation, and what would happen is it would generate its own model of reality. So it would decide the way, it would understand the way things operate in the simulation, and then it will create its own model of reality and a set of ethics based off of what it sees. So yeah, it's a lot of stuff. Anyone have any questions about that?
Did you look at all at Lipson and Schmidt's work on evolutionary programming? I don't know if you're familiar with that.
I did not. That would have been helpful to know.
Yeah, so they basically came at it from a different angle. There were guys at Cornell who now have a startup in Boston. You may want to go meet with them. But they basically took historical data sets and then had evolutionary algorithms run on them.
Yeah.
And in the course of a couple of days, they basically proved out Newtonian laws, right? So they were able to discover through basic mathematical functions. So they went at it from a data set perspective and said, here's the real world, right, of a pendulum swing or a double pendulum swing, and then watched that over and over and over and did a lot of the sort of where you're pushing the button, they used actual data. So
Yeah.
an interesting evolution might be
Yeah,
to
that's something
equip
that-
sensors on actual walking.
Yep.
Right, and then use, tweak your algorithms or work with them on some algorithmic kinds of dynamics to do that kind of evolutionary work based on
Yeah.
a physical data set.
Yeah, so that's something that would change with the, digitizing the whole thing, is that you don't need sensors because it's all built into the program. Yeah, so it's all built into the program. Something that I would do with this, for a simulation like this, is because there's no more physical limitations, you can accelerate the time frame. So teaching this thing to walk might take 13 minutes, it could take an hour, it could take 10 hours depending on how well you want it to walk. But with an artificial intelligence in a code, if you make the time frame of that simulation go at 20 times or 100 times or 1,000 times the speed, what will happen is you'll press a button and 5 seconds later you'll have something that's really, really good at doing that one thing. So if you were to make that program, put it in a supercomputer, load like this game, which is Total War, and if you were to load that into it, accelerate the time frame, walk away, come back a day later, and now you have the greatest Total War player in the world, because it has now done that game, and exclusively that game, for its entire existence, but that entire existence in that simulation is 40 years.
Are we gonna get to see it go?
No, the chips are fried.
What got you interested in artificial intelligence to begin with? Like, what's the allure to you?
I had no idea.
It's just something about it.
What's that movie that just came out, Ex Machina? That was cool. Ex Machina? Ex Machina. I don't know if anyone's seen that, it's really cool. And I just kind of been like interested in artificial intelligence since then. And like, I was in the car like a while ago, we were going to like Worcester or something like that. I was like, why don't they just do this? And I was like, all right, I'll build that. But the robot was just kind of a way to test if this form of artificial intelligence could work. It seems like it does. I mean, I built it. So, I mean, that's the first step. The second step would be to create a new programming language capable of rewriting itself. Teaching that programming language how to program in its own language, and then putting it in a simulation. I don't know how to do that, so I'm just going to learn it. I'm going to do it. And then you can hear about it in the newspaper. Probably as a mad scientist goes insane. What I learned, let's talk about what I learned for a second. So, this is cool, right? It's a freaking robot. Remember that? Yeah. So I learned a lot about robotics. So I would start with linear actuators. I made it off of bipedal leg structure.
Why didn't it just like fall over when it walks? Does it have like a...
Oh, it will. It will. Yes. That's why it's standing up like that.
So, but when it's moving, can it like go all by like without falling over? Does it have something like a calibration kind of?
No. As I said earlier, its model of reality was essentially just a flat plane. So it's not going to be anticipating anything happening in the terms of what it's walking.
So it's just how you make it move. It can just stay standing while it's walking.
Yeah.
In the
There's no-
early phase of development.
In the early phase of development, there's like no sensors on this, like whatsoever. So it's not going to know. Yeah. So it'll just do whatever works, and it decides whatever works depending on what I tell it works.
And you just like turn it on and then it just goes? Or is there like something you can control?
I'll turn it on, and what'll happen is it'll probably do something really stupid, like and just fall over backwards. And I'll say, you can't keep doing that. It breaks the robot, does bad stuff. And I'll say, okay, what about this? And it'll probably do something else that's really weird, and then do the same thing and fall flat on its face. And I'll say, okay, don't do that. And it's like, okay, let's do this. And it walks in, steps one step forward, and it just falls over from there. And I'll say, okay, you're onto something here. And then what will happen is it'll say, okay, do it again, but let's try it a little bit differently. And it'll create a couple sets from that, and I'll say, okay, that one worked the best. And it'll say, okay, let's make something based off of this set, and it'll do something
Then it
else.
just keeps
It'll just,
improvising.
it keeps getting better. It will keep learning based off of what I tell it to do. So yeah, learned a lot about robotics, learned a lot about these stepper motors. Not a whole lot of circuitry that's actually involved. It looks messier than it is. That's just because driver boards suck. All this sucks, but it's fine. So yeah, there's buttons, there's driver boards, and you know, you learn how to make things that move based off of this project. And I'm probably going to be, if I make another iteration of this project, probably going to be a lot better at it. This is the first robot, like, Ed Robotics is new. This is one of the first robots that I've
And
ever
this
built.
is hardware, not software. Would you like better?
Software, infinitely better. I like the software better. That was annoying.
Are you
I had so many like cuts and chemical burns on my hands. It's ridiculous. For really building it.
Are you doing statistical correlations across the variable types? I'm interested in how the learning is actually occurring and being stored.
Yeah.
So are you doing averaging, standard deviations, Bayesian, like?
Or it'll take like a single integer and it'll like multiply it by 1.5 or negative 1.5, and it'll just make there's a random set that's kind of like the step before, and it'll do that across all variables, and every time that it runs through it, it'll do it times 1.4, 1.3, 1.2, and it'll just constantly, drop that. Okay. It'll constantly lower that the range in which it creates new sets of information, and then all these sets of information are stored in arrays, and then it'll run those arrays at the end of each generation.
So are you trying to take one variable at a time and isolate, and then let's say you have a primary variable and you've got 3 others that you're trying to correlate versus that one. If you think you're on a thread of success for variable 1, are you then trying to correlate variables 2, 3, and 4, or are you sort of doing a random walk with your thread of success?
It'll correlate all the other variables. So they're all set in a function that are more or less similar to themselves. But it'll create those actions based off of what's been working. Programming. I learned a lot about programming. So yeah, 7,000 lines of code is really kind of easy. Yeah, so this is
latex. What's latex?
I have not heard of that one either. So this one, C++, the comic is, I asked for 1 copy, not 400. 7,000 lines of code. Ha 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 ha. Yeah, it's more or less. A lot of this I just learned as I was going along. I had an end goal in mind, and I know more or less how I wanted to accomplish that. But every time that I would like try to do something, something else would come up, and I would have to learn how to do it differently, and that would involve different syntax. That would involve different operations. That would involve things that I don't know how to do. So I would look them up. I figure out what other people are doing to solve similar problems, and then I do that. So one of the things that I didn't know how to do was form arrays in C++. I know how to do it in Java, but you really just kind of learn as you're going. It's just kind of a bad sentiment when you're trying to build an artificial intelligence, but it works. So relatively, what's the mechanical aspect is, not as good as the programming one. It doesn't have any bugs, which is good. It uploads. So I know that whatever is in that code, it seems to be working. So yeah, there's a lot of any questions? That's the last
I
slide.
think it's amazing. I'm very impressed.
I think your motivation and your drive is very inspiring.
Thank you.
Nils, did you just use C++ or was it layered code? So for, I know that you can use Python in conjunction with some other codes. Was it just C++ or?
Well, it's said this earlier.
Did you say it earlier?
No, there's this whole thing. It's C++ with, it's C++ syntax in Arduino code. And everyone was like, we don't know what that means.
I don't either, I just know that you can layer the different codes, but.
I actually did not know you could do that.
Nils actually asked me if we should print out the code.
I think it'd be great for everyone to just see it.
We're just thinking like,
I can
like a
show,
ring of
I'm going to
paper.
show you the code right now.
Okay.
I think the actual finished setup code is on my computer at home. I didn't upload it to Drive yet. I think it's still there. But this is the 6,200 line version of the code that went through a couple different iterations. So it takes a little while to load. It takes 5 minutes to copy and paste it. It also crashes the computer. For long, I couldn't store the code on the actual microcontroller because there wasn't enough room on it. And even that was with the Arduino Uno. And then I'm also pretty sure that the Arduino Uno probably couldn't handle the processing of the code. I don't know how big those CPUs are. I might try this with like a Raspberry Pi or something with a little bit more room.
Nils, while you're downloading the code, did you get the equipment that you used? Where did you get that, like the microprocessor and all that? Was that something that the school had, or did you have to research it and find it yourself?
Well, I basically redesigned this a few times over the last semester. And each time that I redesigned it, I would take out another fundamental aspect of it. Like, there used to be 4 sets of motors. I did redesigning, and now it's only 4. And there had to be motors here, so I used a gear system instead. The driver chips, I looked up. Finding those was a little tricky. So it's essentially just the microcontroller, driver chips, 4 sets of motors, and 3D printing. That's absolutely everything that's in here.
And did you actually, okay.
And you used our school's 3D printer?
Yeah, I have my own 3D printer
Uh-huh,
at home that's been running nonstop for about a week.
wow. And then, wow.
Yeah, so, I mean, the school gave me...
Did you study the physical part of the leg and the...
Well, yeah, I did.
all that,
I did.
Designed it off of that?
Yeah, there's quite a bit of geometry that's actually involved in this. It's actually designed so that the center of weight is between and over the 2 feet, and that's why they're extended backwards, so that it actually has a nice center of gravity. The problem is that center of gravity is very strong. The motors are very heavy, but the prints are actually very, very light. It has a very low infill density, meaning that most of those pieces that you're seeing are hollow or almost hollow. They actually hold up rather well. So this is the actual code. This is only 148 pages. This isn't the final one. Okay, so these are actually some of the variables. So each one of these holds 8 variables. I think the final actually holds 12 in each of these, because I forgot I added the delay function. There's a lot of these, and then it begins to correct them. So this is just a single action in a single generation. So what it'll do is for each of the motors, it'll randomize the, I think A1 Gen 1.0 is speed. So it'll initialize, it'll change the speed, change the distance, it'll change the delay, and we'll move on to the next thing. And we'll do that a few times. And then it'll, in between each time it does that, it'll run it. Boop, 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 boop. And this is the actual set of instructions that it creates. So this is between each generation. This is, it runs the set of instructions, and then it waits for about 5 seconds, and it'll run that next set of instructions, and it'll create the calculations, and then it'll run it at the end. And then at the end, it'll...
Did you explore recursion? Are you familiar with the concept of recursion?
I'm not.
In code? So recursion basically lets you do nested or embedded loops. And so you might be able to compress this code substantially by using recursion, because it basically does loops inside of the loops, and you can use classes to do recursion inside of other classes.
I was trying to figure out a way.
Yeah, as you think about that, sort of studying up on recursion and various classes, and I don't know if you confronted vectors at all, but vectors are arrays of indeterminate length, variable length. So depending upon what kind of information you want to include in an array, you can use a vector
Okay.
class. So anyway, there's a bunch of things you could probably do to.
Is that with C++? Is
What's that?
that with C++?
Yeah, C++ is a vector class, and, oh yeah, for sure.
Yeah, okay.
Yeah. So you could probably make it
A lot shorter.
really tighter
Yep.
with a lot of recursion.
Yeah, I'm always trying to figure out how to do that. I knew that the concept was out there, I just didn't know how to do it.
Yeah.
I'm still actually quite a novice at programming.
No, it's awesome what you did, but
Yeah.
I'd research that because
Probably
it'll be your new friend.
Yeah,
I think we got time for maybe 2 more questions.
yeah.
So, there's a bunch of people who are not seniors here, and I'm wondering if you can offer some suggestions or opinions about senior projects and what they might consider.
Do it. Yeah, I really can't stress those enough. I've been doing basically school programs for the last 3 years. I took both of the robotics freshman year. I took programming 1 and 2. But there really is only so much that this school can give you with what you want to do. So if I wanted to do, if I was like really into like cooking and culinary stuff, I might be able to take culinary after school, but I'm not going to be able to like test out recipes and try my own things until I create a project and I decide to do those things. You should definitely do a senior project. You should definitely do an independent study because it can sort of tailor what you want to do. And something with this project, I'm actually declared as an electromechanical engineering major. The reason I did that is because I don't know what engineering that I wanted to do, so I just did all of them. So with this project, what I really figured out that I wanted to do was more the programming aspect rather than the physical aspect. So with that regard, I'll probably go into computer sciences or programming or something like that, rather than mechanical, maybe even electrical. Yeah, you just figure out what you like to do and you just do it.
So piggybacking on Mr. Connor's question, did you talk about one of the highlights of this experience for you, and then one of the frustrations that you encountered that you would want somebody to, you want to tell the juniors in case they ran into the same problem? You persevered and you worked through it, and you came up with this amazing project, but a lot of kids get stuck on that one problem.
I would say try to go for as many problems as you can. The more problems, better, because you learn how to fix those problems. I went through numerous problems. I would recommend it. The first problem, or the most major problem that I ran into was after I finished the code, I realized it had to be repeated with 20 more actions. That was a lot of code. That was a lot of things that had to change. That was a lot of time that I put into this that I'm not getting back. A lot of problems with the machinery. There was a lot of redesigns. There was a lot of things breaking, things not working. But ultimately, what doing this type of project does is it teaches you how to deal with those problems. So I would say do something completely outlandish, something that probably won't work, but if it does, it's awesome. And if not, just try something else. Fix it. Do better. That is how you learn.
And how many weeks have you been working at this? You said 10?
Quite a few.
Or more than that?
Well, I've been working on like designs and stuff like that for the whole semester. Every 3 periods, I'm here coding, designing, doing something else. Wasn't until a few weeks ago that things actually started getting built. Yeah.
All right.